Hello and welcome to our first webinar on finding limits graphically and numerically. This is the first first section in calculus, and so we're going to start with a little background knowledge from pre-calculus. Our goal here is to find the limit using numerical and graphical approach and learn different ways limits can exist or fail to exist. So we're going to start with talking about sketching a graph, and you can go ahead and pause this and do the in. I'm going to just go ahead and work on this, but that's kind of the way it goes. As we get to an example, I would suggest that you pause the example and try it yourself, and then move along and watch the video and see how I did it. So first thing it says to sketch the graph. So that's the first thing I'm going to do is sketch the graph. Actually, no, I'm not going to sketch the graph first. I'll come back to that. I'm actually going to first talk about state all the important information about the graph: asymptotes, holes, intercepts, things like that. So by looking at this graph, I can see that on the bottom, if I was to write this out in factored form, I would have x minus 2 times x minus 2 on top, and on the bottom I'm going to have x minus 2 and x plus 2. So knowing this right here, this x minus 2 over x minus 2 becomes a hole in the graph. So I have a hole in the graph, a hole at x equals 2. If I set x minus 2 equal to 0, that's where I get my x minus 2 equal to 0. That's where I get my hole at 2. Then I have x minus 2 over x plus 2 as the remaining function after I reduce this function. And one of the things that we do a lot in calculus and a lot of math is we come up with representative functions that represent basically the same thing, but this is without the hole in the graph. So you'll notice that on the bottom down here, if I set x plus 2 equal to 0, then I end up with x equals negative 2, and that means if I put negative 2 in for x on the bottom, or actually into this function, the bottom becomes 0 and it doesn't exist. So that means we have a vertical asymptote there. See there, vertical asymptote. And so that's at x equals negative 2. X equals negative 2. And one more time, x equals negative 2. And so then we have, you'll notice that if this thing was multiplied out, if I multiply the top out, I get x squared. I'm going to go back to the original function, x squared minus 4x plus 4, and on the bottom, multiplied out is what you're looking at, x squared minus 4. And if that's the case, then x squared and x squared are the same power, same highest degree, and therefore the leading coefficients gives us a horizontal asymptote. So we have a horizontal asymptote that is 1 over 1, because those are the leading coefficients of the highest power, which means I have a horizontal asymptote at 1. So if I go ahead and sketch this graph, and we should go ahead and set this thing equal to 0, and if I set it equal to 0, if I set x squared, x minus 2, squared over x squared minus 4 equal to 0 to find my intercepts, find my x-intercepts, this bottom part will multiply across and become 0 times it. So I really have x minus 2 squared equals 0, and then if I square root both sides, I end up with just x minus 2 equals 0. So at x equals 2, I'll be crossing the x-axis. So this is x-intercepts. That's really what we're looking for there. So even though there's going to be a hole there at x equals 2, that's going to look like it's crossing the x-axis there. So let's take a look at what the graph looks like of this thing. And basically, if I say x minus 2 squared divided by x squared, make sure you use parentheses, x squared minus 4, all these things should show up on my graph. There's my graph. Let me move it down here so we can analyze it a little bit more, and we'll come back to it in just a second. Alright, you can see there's a horizontal asymptote at 1. The graph is getting close to 1 as it goes out on the ends. It has a vertical asymptote at negative 2 over here. That's what this vertical line is. And I bet if I look at the table, you can see my only x-intercept is x equals 2. But if I look at my table on my graph, and if I look, and let's do my table set. started at 0, 0 and count by ones. If I go to my table set and look at 2 there, you can see when x equals 2, there is an error in the graph. And so that is the hole that appears, and it's also where it looks like it's crossing the x-axis because it goes from a negative to a positive. So that's all the information from that, and that's things that you're going to need to know as we go through this section. So let's move on. And so here's the first one, and they're asking you to estimate the limits numerically. And basically what you're trying to do with this guy is trying to find out what happens as we get close to 0. Because look what happens. If I put 0 into this function, I'll get 0 on top, and on the bottom I'll take the square root of 0 plus 1 minus 1, which gives me 0 on top, and then the square root of 1 minus 1, which is really 0 over 0. So we don't know exactly what's happening here at 0. We got to figure out what's happening as we get close. And so this is going to be estimating a limit as we approach 0. And so basically we're going to go through and we're going to use these values. We're going to plug these values into this function, and you'll notice the values get closer and closer to 0 as I go from either side. So I just need to figure out what's happening, and probably the best way to do this is to either graph this function up here and use the table, or the other way, and actually that's the way I'm going to do it, or the other way is just to type this function in over and over again. So what I'm going to do is I'm going to start by setting this graph, putting this graph into my function here. And as we start this, probably your best bet is to go ahead and graph all of functions until you get used to what they look like, because some of these functions are quite funny looking and we just don't know. It's just one of those things that the more you graph, the more you see, the better off you'll be in this class. So there we go. So now I've got that function, and if I graph it, it looks something like that. That doesn't help me much, but you can see as I'm approaching, I got to find out what's happening as I approach the 0 value. It looks like there's a number there, but we're gonna use the table to help us. So go to your table set, and this time I'm going to start at 0, but I'm going to go make it count by negative 0.01. Basically, these values right here. It's just, and that's where. And actually, I'm going to start at that value, at arrow up, and say negative 0.01. So I'm just using this value over here, and I'm going to see what happens at my graph. And so you can see at negative 0.01, it ends up with 1.995. 1.995. Well, if I go to the other side and go to positive 0.1, and so I'm just going to arrow up here. There it is, 0.01, positive. You can see there's still an error at 0, so we don't know exactly what's happening. At positive 0.1, it looks like it's 2.005. 2.005. Alright, so now make it easier on ourselves. We're going to go back to our table set, and this time my table start is going to be the negative version over here of negative 0.001, and that's what I'm going to count by too, negative 0.001. And so now if I go to my table, you can see that I get, looks like an extra 9 in this one. So I get 1.9995. And so then if I arrow over on my graph to the positive side of it, you can still see there's an error. You can see that I pick up an extra 0 for my y value. So 2.0005. Well, let's go one more. And you can probably make a guess at what's going to happen at 0. But this time I'm going to go to my table set, and I'm just going to insert another 0. Insert a 0. Oop, not there. Well, that's fine, but not there. Insert another 0, so I have 3 zeros. And then down here, I'm going to do the same thing. Insert another 0. Instead of typing it all over again. And so now if I go to my table, I end up with, it looks like, well, there it is, that number right there. It looks like it should be 1.9995. It's an extra 5, an extra 9, and this guy, it gets an extra 0, and you could see it on the graph. Let me go back to it. The problem is our graphing calculator, if you type these in, your graphing calculator would give you more zeros. But that's basically what happens. And so you can see as we're getting closer and closer to this 0, even though there's nothing there, we get a value of 2. And that is what the idea of a limit is. It doesn't have to have a value at that point that you want, but it is what's happening as you approach it. Now we have new notation that goes with this, and so we're going to use limit as our notation, and we're going to say as x approaches 0, because we want to know what's happened as x approaches 0. We're going to say x over the square root of x plus 1 minus 1. Well, we found out by using our table here that it approaches 2. And so basically a limit is find out what the y value is as we approach some x value that may or may not be in the function itself. And so 0 was not in the function. It caused an error. But as we approach it from both sides, from the positive side and from the negative side, we got really close to 2. So we can say that as for this graph, that 2 is the limit of that graph. So that's basically what all of this says. This is the same thing. It's the solution. And so if you saw the graph that I showed you earlier, this is what the graph looks like, and this is just some things that you need to realize is probably the second thing down there. Even though the graph approaches 0 from both sides, and this happens a lot, is that you may or may not have a value which we call c at that point. And so if c is what is the y value or the x value, and as in this case c was 0, if there is a value there for y or not, it doesn't matter, because that basically what we're saying is it has no bearing on the existence of the limit if there is a point there or not. So because that point wasn't there, we approach the same value from both sides. We approach 2, the y value, from both sides, even though 2 is not actually on the graph at x equals 0. It doesn't matter. We just care about what's happening as we get closer and closer to it. And that's the idea of a limit. So then we have an example 2 here, and we want to find the limit as x approaches 2 in this function. And so I'm going to, I'll shrink this graph a little bit. And so I'm going to change the notation just to show you what a limit notation is for this. So you'd say the limit as x approaches 2 of, I'm going to use f of x because I don't feel like writing that whole thing over again, but we know f of x is this thing right here, okay? And that's what we're dealing with. So if we say f of x is 1 as x, for any y is 1 for any value of x except for when x is 2. So basically I have a line that looks like this. So the y value is 1 except for when x is 2. So I have a line that does this, and I really have a line that skips that little spot and goes this way. So there's a little hole or something in there that is missing at 2. And I don't want to make it that big, but we'll do that. And so we have this open spot at x equals 2, which is basically what this is saying up here. So then, when x is equal to 2, we drop down to this point down here. Well, now we have a value at x equals 2. So what is the limit? Well, again, remember, limit is what happens as we approach the x value of 2 from both sides. So as we look at the graph, when we approach the x value of 2, we're approaching along the red line that I drew there. And that means that basically we are approaching the value of 1. Even though the value is 0, it doesn't matter. The value of this graph as we approach it from both sides is 1. This point, whether it's there or not, has no bearing on the graph itself, on the limit itself. And so that's something we need to keep in mind. And so you can look, we'll go through this. This is a little bit different graph, but that was a little bit different graph, but it's still the same idea. The limit is still 2. The limit is still 1, even though the point is somewhere else. And so the only difference is they said it was 0 when x was equal to 2. Same idea, though. So then what happens